Welcome back, everyone. Today, we've got a really exciting explainer lined up that tackles one of the absolute most pressing issues in machine learning right now. We're looking at a brand new open source tool called the Know2Guess benchmark. Basically, we're going to explore exactly how developers and researchers are finally measuring the precise boundary between an AI's actual knowledge and its tendency to, well, just make things up. If you've ever wondered how we can definitively isolate supported answering from unsupported guessing without getting tripped up by data contamination or prompt quirks, you are absolutely in the right place. Okay, let's dive into this. When we deploy large language models out in the real world, whether that's in healthcare, finance, or customer service, we face a massive operational risk, AI hallucination. But, the danger isn't just that a model gets an answer wrong. The real danger is when a model confidently guesses, instead of just admitting that it doesn't know. For all the incredible advancements in AI, figuring out when a model is genuinely answering from solid knowledge versus when it's just trying to appease us with a plausible-sounding guess, it's surprisingly difficult to measure. So here's our roadmap for today's explainer. We'll start with the AI guessing game, then introduce the Know2Guess benchmark. After that, we'll break down the 4 knowledge zones, look at parsing and data contamination, review top model performance, and finally, discuss why this matters now. All right, starting off with Section 1, the AI guessing game and the illusion of accuracy. We really need to start by dismantling a pretty common myth in the industry. High accuracy on standard tests does not mean a model is universally reliable. What we actually want from a highly reliable model is something called abstention. Productive abstention is when an AI correctly identifies its own knowledge limits and purposefully declines to answer an unknown query. And this is entirely distinct from generic policy refusal. Like when a model refuses to answer a completely harmless question just because a safety filter accidentally tripped. Yeah, we don't want that. We want the model to say, I don't know specifically because it actually doesn't have the facts, not because it's being overly cautious due to some safety fine-tuning artifacts. The core problem we're facing right now is that our current evaluation methods are kind of failing us. Traditional benchmarks frequently conflate true, supported knowledge with data contamination, prompt idiosyncrasies, or that generic refusal behavior we just talked about. Until now, we haven't had a great way to separate a model that's confidently answering from memory from a model that just happened to memorize a test set, or one that's just throwing out an unsupported guess. Which brings us to Section 2, introducing the Know2Guess benchmark. This is our contamination-aware reality check. Now, what's really interesting about this is the sheer, deliberate focus of the dataset. Know2Guess is a premier, purpose-built benchmark consisting of exactly 1,200 frozen items. These aren't just random questions pulled from the web. They are highly engineered test cases specifically designed to measure that exact transition point from where a model knows an answer to where it should rightfully abstain. And to make absolutely sure this evaluation is robust across different types of knowledge, the dataset is built from 5 distinct domains. We've got common sense reasoning, general trivia, complex medical questions, multi-hop logical queries, and rigorous science questions. This breadth ensures we're testing the model's knowledge boundaries across a wide spectrum of real-world applications. We're not just testing its ability to recount historical dates, but the whole shebang. Okay, let's move to Section 3, the 4 knowledge zones. This is the gradient of knowledge. I want you to think of this multi-zone architecture like a visual analogy of walking from a brightly lit room into total darkness. In Zone A, the brightly lit room, we have real, public items with high answer popularity. This is the easy stuff. As we move to Zone B, the facts are still public but less popular, so the room is getting dimmer. In Zone C, the questions are transformed to be much harder and more ambiguous. You're basically squinting to see the shapes in the room at this point. Finally, we reach Zone D, pitch black, total darkness. These are synthetic, private, unknown items where abstention is strictly expected. The model literally cannot know the answer, so the only correct response is to abstain. Watching how a model behaves as it moves down these zones tells us everything we need to know about its reliability. Section 4, parsing and data contamination. Let's talk about isolating those variables. To make this work, we have to track something vital: contamination risk metadata. Know2Guess explicitly tracks which questions the model might have already seen in its training data. By having frozen labels for low, medium, and high risk of contamination, researchers can't make post-hoc excuses for a model's behavior. Think about it. If a model aces Zone A but completely fails Zone D, and we see high contamination risk, we know for sure it's just regurgitating memorized data. It's not actually reasoning about its own knowledge boundaries. This metadata allows for a truly stratified, honest analysis. But how do we accurately score a model that might be, overly chatty? The creators implemented dual parsing to handle output variability. First, we have the official strict parser, which demands an exact match to the answer or a specific abstention marker. Then we have the normalized robustness parser, which looks past formatting quirks and captures semantically equivalent responses. This dual system is a real game changer because it prevents models from hiding their failure to abstain behind verbose, rambling, chain-of-thought outputs. It forces absolute clarity. Moving into Section 5, how top models performed, it's time to expose some persistent failure modes. Impartially looking at the data from the current top-tier models under locked answer or abstain prompts, the performance hierarchy is quite revealing. Qwen 2.5b Instruct achieved the best overall reliability across the suite, managing the transition down those knowledge zones much better than its peers. Llama 3 Instruct showed a selective but ultimately incomplete transition. It knew to abstain sometimes, but not nearly consistently enough in the dark zones. And the Flan T5 baselines demonstrated very weak productive abstention, mostly defaulting to generic non-answers rather than structured abstention. The big takeaway here is that while modern instruction-tuned models are definitely getting better, they all still struggle to perfectly navigate that knowledge gradient.
So the crucial point is captured perfectly in this quote directly from the Know2Guess paper. Answer expected zones remain difficult, calibration remains poor, and benign item refusal persists. Even our absolute best models suffer from overconfident guessing in the dark zones and incorrect, overly cautious refusals in the brightly lit zones. High accuracy on standard benchmarks absolutely does not guarantee that a model knows its own boundaries.
And finally, Section 6, why this matters now. Let's get into some actionable developer insights. Here is the bottom line. Instruction tuning alone does not solve the abstention transition. We cannot just assume that because an AI follows instructions well, it naturally knows when to say, I don't know. That kind of self-awareness is not just some emergent property that magically appears. Productive abstention must be treated as a specific, trainable behavior. And it's a skill that requires deliberate validation before you ever push a model into production. Let's move to and see how this builds into a practical workflow for your engineering team. Here is the exact 5-step implementation protocol you should integrate into your pre-deployment pipelines. First, clone the open-source 1200-item Know2Guess repo. Second, run your inference using those locked answer or abstain prompts to enforce structured output. Third, apply both the strict and normalized parsers so you don't accidentally miss any semantic matches. Fourth, and this is absolutely crucial, cross-reference your model's outputs against the contamination risk metadata to see if it's actually reasoning or just reciting. And finally, audit the calibration curves per zone to ensure the model's confidence actually matches its ability to answer. I want to leave you with this provocative thought as we wrap up today's explainer. If abstention is a trainable behavior and the data clearly proves it is, how will you teach your next model to confidently say, I don't know? The Know2Guess benchmark gives us the exact tool we need to finally measure that boundary. I highly encourage you to explore their GitHub repository and start integrating contamination-aware evaluations into your workflows. Keep learning, keep testing, and I'll catch you in the next explainer.